Hello and welcome back to AICE Chemistry Lecture Series. Today we're going to start our discussion of Chapter 4, which focuses on chemical bonding. Now, throughout this discussion for Chapter 4, we're going to talk a lot about not just bonding as we saw it in honors chemistry, ionic, covalent, metallic bonding, and those kind of topics, but also bonding at a much wider level and in the scope of the AICE Chemistry exam. Now, this chapter does have a lot of sections. There are 9 different sections that we're going to go over, all of which have to deal with some aspect of chemical bonding, starting with some basics of bonding in general, moving on to ionic bonding, which is a more simpler type of bonding that we're going to see. And then moving forward to covalent bonding, which has a lot of different subtopics, such as the shapes of molecules or best pair theory, pi and sigma bonding, which is a new topic we're going to discuss this year. Metallic bonding moving after that, so a different type of bonding, which we did cover to some basic extent in honors chemistry, but we're going to discuss it more in depth now in AS. And then we'll move forward with other aspects of covalent bonding that happens between molecules, such as intermolecular forces and hydrogen bonding specifically. And then finishing our conversation with how any of these types of bonding affects properties of the compounds. So let's start with section 1, and let's talk about the types of chemical bonding. So these sections will be very brief. It's just a short overview of what chemical bonding is and what the different types of chemical bonding that we're going to discuss in this chapter are. So let's talk about types of strong bonds. Now, why do we use this terminology here, strong bonds, as opposed to just saying bonding? One of the things that you will realize as we go through this chapter is that we have to change the scope of how we talk about bonds and intermolecular forces in this year. Because at the end of the day, all anything is, whether it's chemical bonds or intermolecular forces is a magnetic attraction. It's a magnetic attraction between positives and negatives. Now, how the magnetic attraction plays out, what it looks like, that's going to change from ionic bond to covalent bonding to metallic bonding. But at the end of the day, all three of these, ionic, covalent, and metallic bonding, boils down to something that's negative attracting something that is positive and vice versa. And then even with intermolecular forces, that is exactly the same thing. It's just a magnetic attraction, just at a much weaker level. So it's all shades of gray here when we talk about bonding, and it's about being able to use the proper terminology for the different types of magnetic attraction. With ionic bonding, the magnetic attraction, or what we call the electrostatic attraction, again, same thing, magnetic, electrostatic. The electrostatic or magnetic attraction is between positive cations and negative anions in an ionic crystal lattice. So with ionic bonding, we're starting with a positively charged and a negatively charged ion, or what we call cations and anions, and them attracting each other. Since cations are positive in charge, let me put that in here, since cations are positive in charge and anions are negative in charge, they're going to attract each other. So the magnetic bonding or the electrostatic attraction that we talk about with ionic bonding is between ions. Now, that is all in the context of forming a large ionic crystal lattice. And this word is very important here. A lattice is a regularly repeating arrangement of atoms, molecules, or ions in 3 dimensions throughout the whole crystal structure. Last year, we only talked about the word lattice in the context of ionic bonds. But in reality, we can talk about lattices, which is a plural lattice, with any type of bonding, as long as there's a repeating arrangement, as long as there is a regular arrangement, a repetition of a structure, it's a lattice. So we can have an ionic lattice, which are the ones that we most commonly talk about, or an ionic crystal lattice. We could have a covalent lattice made out of molecules, or we could have a metallic lattice made out of cations and a sea of electrons. So we'll talk about a lattice, and you will hear this word a lot, because in reality, most compounds in existence, when they're solid, exist in the form of a lattice. It's just what type of lattice are we looking at that changes from chemical to chemical. So that's ionic bonding. It's a lattice, but this particular lattice has ions, cations and anions at its that make it up, and the attraction between those anions and cations is what makes up that ionic bond, that electrostatic attraction or magnetic attraction between cations and anions. For a covalent bond, covalent bonding happens when bonds form when the outer electrons of two atoms are shared. Now, why is covalent bonding also an electrostatic or magnetic attraction? One of the things that you might not realize is that even though the electrons are shared, that magnetic attraction caused by that sharing is what a covalent bond is. If we have two nucleuses or nuclei, so we have a positive nucleus here from one atom, and then a positive nucleus here from another atom, and then we have the atoms as a whole, and I'm going to draw them as circles, kind of oblong circles here. Move this nuclei a little farther in. If we have electrons here that are being shared by these two atoms, what is keeping these two atoms together is not just a physical sharing of electrons, because physical sharing does not actually keep atoms together. What keeps these two atoms together, if they're sharing electrons, is that the nucleus of this atom is attracted to the electrons that they're sharing, and the nucleus of this atom are also attracted to the electrons that they're sharing. So again, it's a magnetic attraction. The magnetic attraction of the nuclei of the two atoms for the shared electrons. So that's kind of how our mentality needs to start changing from last year. Last year we saw in honors chemistry that the covalent bonds are sharing of electrons, and we thought of it more like a physical tether, a physical bond that kept these two atoms together. But in reality, it's not the physical act of sharing the electrons that keeps the atoms together, but the magnetic attraction formed between the nucleus of the atoms, or the nuclei, because it's plural, of the atoms, and the shared electrons that are between them. That's what's keeping these two atoms together in a covalent bond. So, ionic bond is the magnetic attraction between anions and cations that keeps the compound together. In a covalent bond, the molecules are held together by the magnetic attraction between the nuclei of the atoms and the shared electrons. And then finally, we have a metallic bond. The metallic bond is the bonds that hold a metal together, and this is done through a sea of electrons. Of electrons. Now, a better word than C, this is what we call the last year, sea of electrons. But a better word instead of C is delocalized electrons. So instead of using this old terminology now, we're going to use the words delocalized, I can't spell, delocalized electrons. And this is a much better word than sea of electrons because it actually gives us an idea of what is happening to those electrons. Now, we're going to discuss this a lot more when we do the individual sections on ionic, covalent, and metallic bonding. But this is just a brief introduction to the three types of bonding. Now, apart from the three types of bonding, ionic, covalent, and metallic, we have van der Waals forces or intermolecular forces. Now, we did not use this word a lot last year, and it is a word that I like to avoid, van der Waals forces. Instead, we use the term intermolecular forces. So, while the bonds that we just talked about, ionic, covalent, and metallic, keep compounds together, so a molecule for a covalent compound, a lattice for an ionic compound, or a metallic lattice for metal, intermolecular forces are the forces that keep molecules together. So let's kind of break down the word here, because the nomenclature of these words, basically the reasoning behind the words is important. Inter means between. Molecular means molecules. forces. So intermolecular, between molecules. Intermolecular forces are the forces that keep molecules together, where bonds, or what we call intramolecular with an A, so intramolecular forces, are essentially just bonds. Intra means within, whereas inter means between. So intermolecular forces keeps molecules together to each other. Intramolecular forces, or what we know more commonly called bonds, are within compounds. So they keep the compound itself together. So while atoms inside of a chemical are held together by strong forces like bonds, intramolecular forces, molecules formed by covalent bonding are held together by weaker forces, which again we can call intermolecular forces, which is my preferred term, or also we can call them van der Waals forces. Intermolecular forces, van der Waals forces, whatever you want to call them, these are the forces that are going to keep one molecule attracted to another molecule. So this is not what keeps H2O together, as in the molecule of H2O. This is what keeps a whole cup of water from splitting up into individual H2O molecules. So it is a much weaker force, but one that does play a key role when it comes to molecular forces. And we'll talk about the distinctions between this a lot throughout this chapter. Now, there are three different types of intramolecular forces, and one that we have to discuss because it might not be intermolecular, but it is something that is worth discussing and happens between ions and molecules. Now, the first type and the weakest type of intermolecular force is a dipole force, otherwise also known as an instantaneous dipole-induced dipole force, or IDID, or a London dispersion force. We learned about these last year, and they're the forces that happen due to the random movement of electrons. We'll talk about them in detail when we do the intermolecular forces section, but know that these are the weakest of all the types of forces. And we discussed them last year. We're going to discuss them a little more this year. One thing that I would like to point out is that while we do use the term IDID in the book and in common everyday speak when it comes to science and chemistry, this should not be an acronym that you use on the actual exam. Instantaneous dipole-induced dipole forces, or just dipole forces, are a better way of saying this, even London dispersion forces. But don't use IDID because it's an acronym that is not necessarily widely accepted. So unless you're going to define it as instantaneous dipole-induced dipole forces and then put it in parentheses, and then you can use it over and over again, I would avoid just in general using this little acronym. The next type of intermolecular force, so that was number one. The next type of intermolecular force is the permanent dipole force. Again, commonly named as PDPD, but we're not going to use that acronym on the exam because, again, it's not commonly accepted. So permanent dipole forces are forces of attraction that happen between polar molecules, and again, it's something that we're going to discuss more in depth once we do the intermolecular force section of this chapter. And then the last type of intermolecular force that is widely accepted is the hydrogen bonding that happens in polar molecules that have hydrogen atoms either bonded to fluorine, oxygen, or nitrogen. And again, we discussed this last year. We're going to discuss it a lot more in depth once we get to the section on intermolecular forces. But these are the three types of forces that we commonly see. There is a fourth force, I should say, which is the ion dipole force. But unlike 1, 2, and 3, which happen between molecules, ion dipole forces, like the name implies, happen between ions and polar molecules. One of the reasons we don't like to call these intermolecular forces is because they don't happen between molecules, they happen between molecules and ions. But out of the four of them, they are the strongest type of force, and they play a key role in the interaction of water with ionic compounds when they dissolve. And we'll discuss that again later in the chapter. So just to summarize, they're bonds or intramolecular forces, which are the type of forces that hold a compound together, versus intermolecular forces, which we just discussed here, which are the forces that keep molecules close to each other, like water molecules in a cup close to each other. These forces do have a hierarchy when it comes to intermolecular forces of strength, with instantaneous dipoles, induced dipole forces being the weakest, followed by permanent dipole forces, then hydrogen bonding, and then finally ion dipole forces. We're going to discuss these again at length in the intermolecular forces section, but they might come up throughout the chapter, so I wanted to make sure you had a good look at the basics of them and at the basics of bonding as well. That is it for section 1. Like I said, it's very short and introductory. Most of this should just serve to have recalled information in your head that you learned last year in honors chemistry, but we will go more in depth into both of these topics of bonding and intermolecular forces in later sections. That's it for this video. I will see you in the video for chapter 2.